Thank you very much for the introduction, and thank you everyone for attending today. I hope you'll find this enjoyable. Now, this is a bit of a background on the evolution of satellite services, not very extensive, but I just want to show you the difference between traditional satellite communication. So what you're seeing here is a coverage patch of one of the typical satellites. These are traditional satellites being there for 30, 40 years. So you can see this coverage patch. If you are anywhere in this region, you transmit to the satellite. This is the transmitter, the uplink. It goes to the satellite. The satellite amplifies the signal. It shifts the frequency and transmitted back to the entire region. So basically, if you're using certain frequency, you're going to occupy the entire patch, or basically entire Europe with this frequency. So what do we deduce here? It's a very low efficiency. So it's very inefficient in using the spectrum. Also, these are covered by geostationary orbits, meaning the latency is at least 240 milliseconds for a round trip. The newer version is called the high throughput satellites. So these utilizes multiple spots. You can see, if you can see the colors here, you have red, green, and blue. And for example, blue color is being reused, meaning the frequency is being reutilized more efficiently. And thus these satellites can provide much higher bandwidth, can provide much higher internet speed. The modern version of satellites, which we call them the mega satellite constellation, we will have more depth on these constellations. We talk about thousands of low Earth orbit satellites. These satellites also have much smaller beam. Mind, this is a reverse engineering from FCC filing. This is a zoomed in version on the US, and you can see one of the OneWeb satellites and the beams of this satellite. Now, other satellites can provide also electronically steerable beams, but what you can notice is that the beams are much smaller. These satellites are much closer to Earth, so we're expecting much lower latency of about 20 to 40 millisecond round trip time. Also, these satellites can be connected to each other, which was called inter-satellite links, which provides much faster internet. We'll dive into more depth in the next couple of slides. Now, just looking at the satellite services in general, we already covered the fixed satellite service. We covered also the high throughput satellites. Now there's another class. It's called land mobile satellites or land mobile services. So basically, these are there are a few geostationary satellites. Also, there are traditional also LEO satellites, for example, Iridium services. And they're not really for high bandwidth, so this is mostly low data rate. It's still acceptable, but they're not designed for heavy internet use. And they are already deployed around the world. There are new services which are called IoT over satellite or Internet of Things over satellite, which are designed for narrowband system. If you have a sensor, for example, sending, for example, few packets per day, and then it also is delay tolerant. For example, you just measure, you want to provide 3-4 measurement of a water tank somewhere in the desert, somewhere in a very far field, that's fine. So it is called IoT over satellites. The newer version, which is the last point here, sorry for the glitch, it's called the mega satellite constellation. And these satellites not only are promising to provide broadband connection, broadband is like the internet connection, talking about hundreds of megabits per second, but also could be used in the future for IoT connectivity and direct to cell applications. So you can use your phone directly to these satellites. This is very similar to the land mobile services. They call them D2D, direct to device or direct to cell. And also promising future integration with 6G services. Now let's look at the opportunities and challenges in mega satellite networks. So here's a simulation of a mega satellite network. So it, well, potentially can provide fair and global coverage. We saw previously that rural areas do not have good coverage, low latency because of the proximity to Earth, better spectral efficiency because we are going to reuse the spectrum again and again in different locations. Spectrum is a very important resource and a finite resource. And also we have low terminal radio frequency power because you are very close to the satellite, so you don't need very high power. And as such, it's lower cost. The opportunity to connect satellites together by inter-satellite links can further improve the coverage because you don't, I'm just going to pause this video. I'll give you an example here. If you have a station somewhere here, you are uplinking or connecting to the satellite needs to have a feeder link towards a gateway. But if there is no gateway within the coverage patch, even if there is a satellite, you can't get internet connection. However, if the satellites are connected to each other, there will be less demand on the ground station or the gateways, which will allow more flexible deployment. Now, I'll give you two examples of mega satellite constellation. I just downloaded the two-line elements, the Keplerian elements of OneWeb. It's about 650 satellites. And I'm going to play the propagation, the simulation of these satellites. This constellation called Walker Star. And here's another example. This is Starlink and a staggering number of about 8,000 satellites. Now, look at this constellation and have a look at these satellites. It looks like a bit random, right? I will come back to this concept of randomness. The other thing that after I simulated this, my computer crashed because it's a very heavy number of satellites. Now, let's look at the challenges in this mega satellite constellation. This is a simulation of a link between Melbourne and a point in Europe. And we are routing the traffic through inter-satellite connections. Again, these are hypothetical internet satellite connection because ISL is still being deployed, is not widely used. And you can note that how the topology is dynamic, unlike cellular networks. So the geometry is very complicated, it's keep evolving. Now the traffic under the satellite, let's take this satellite, for example, it passes over Australia, over Melbourne, for example, a very highly populated area, but then it goes nowhere. It goes on top of the ocean, and practically it might be one or two ships in this area. So the traffic will jump from very, very heavy traffic to very light traffic. There's a high dynamic traffic. Now, integration with terrestrial network is very challenging because if you're going to use same frequencies, you have to coordinate with not only with Australian operators, but with international with all operators around the world that are subscribing to the service of integrated satellite and terrestrial services. The other thing is the radio channel losses, because in terrestrial application, the maximum distance to your cellular tower or the typical distance to your cellular tower between 500 to a few kilometers. But with these satellites, we're talking about distances of a few hundred kilometers. So the path loss is much larger. Also, the coverage spot is much larger. Now, also we have high Doppler shift because these satellites are moving about 6 to 8 kilometers per second. And that results in a very high Doppler shift, which we need to mitigate and compensate for. Now, network security obviously is a very big concern because these satellites can be jammed either intentionally or could be interfered unintentionally. There's also the coordination between the spectrum use of these low Earth orbit satellites with existing geostationary satellites. Now, spectrum cannot be created. It's a finite resource, as we said at the beginning. So you have to provide this coordination. Now, there are other challenges we're not going to cover, but in general, also the creation of space debris should be managed very carefully. These satellites are, they have hazards of collision. There are thousands, tens of thousands of collision avoidance maneuvers being initiated in some of these constellations. We also want to guarantee that the fairer access to LEO orbits, the constellation shouldn't be controlled by just one company or one person. It should be more democratized and everyone should have a fair access to space. I'll give you a few examples of challenges in satellite. So this is an example of interference. It's not a satellite, it's just a drone, but I want to show you the packets. So the x-axis is frequency, y-axis is the time of collection, and these little squares means there is a transmission being collected. This is just to let you know, this is called the ISM band, and these are IoT traffics, most likely electricity meters. Now, this is at height 18 meters. Now, if you go to 60 meters, what you note are much more packets. And if you go just 100 meters, you can see that the number of packets just exploded. And you can imagine when you go 400 kilometers or 300 kilometers, the number of packets that a satellite will be seeing. So there will be enormous interference towards the satellite. Another example of the challenges are the radio channel conditions. This is a actual recording from a site called Chilbilton in the United Kingdom. The data is available publicly. What you note here, the x-axis is the time, y-axis, we call it the excess path loss. So this is the additional path loss on top of the free space path loss. So 0 means there is no additional loss, but then note here at some point, the losses were around 10 decibel, and another point, the losses were about 20 decibel. Now, anyone working in the telecom industry will know that a 20 decibel is basically a link failure. Nobody designs a link with a 20 decibel of power margin. So what does that mean? Why this happened? Because of rain. At this particular frequency, this was about QV band. There was a rain bursts at these two events, and the rain caused very high attenuation in the link. So if we're going to use higher frequency bands, so for example, the C band, about 4 gigahertz KU band, 10 gigahertz KA, and so on. Now, as you go up and up in frequency, it would be freer. There would be more room. However, it would be more challenging to use it because it's very susceptible to rain fading. So when we use direct-to-device communication, we need to be very careful as well of the line of sight availability. We're going to talk about this in the next slide. Now, for other applications, for example, this is called the L and S band. This is 1 gigahertz, around 1 to 2 gigahertz. These are more suitable for direct-to-device communication because you do not need a very highly directive antenna. So when you hold your mobile, you don't want to orient it towards the satellite to receive a signal. Now, you can still use higher frequencies, obviously, but these are preferable for mobility. These are also challenging in urban environments. So let's just give you a difference between terrestrial channel. Terrestrial channel, this is your telecom tower. Here's your device. The channel is homogeneous, meaning the clutter here, buildings, houses, trees, etc., they are homogeneous across the environment, while for satellite, it's quite different. Signal travels for a few hundred kilometers in free space, in vacuum, there's no problem with that, but then it reaches the last 30 meters with very heavy losses, which depends on the angle at which the signal is arriving. Typically, the channel fluctuates between a good state and a bad state. Good state mean when you have a line of sight, approximately bad state when you do not have a line of sight. For this line of sight challenge is very important. This is an example. These are practical measurements we've done for the line of sight. So basically, we put a camera on top of a car and drove around Melbourne as an example of a metropolitan area. So you can see this is the azimuth. So basically, it's a 360 degrees from the heading of the car to left and the right. And this angle, the y-axis, is the azimuth. So basically, the line on top is the zenith, is the point just directly above the car. Now, because the sky is very bright, so you're able to binarize the image. Everything in black you're seeing is a blocked sky. Everything in white is a non-blocked sky. So if a satellite exists in this area, you should have line of sight with it. I'm just going to play that just to give you an example of how the environment would look like in a typical city. So for non-terrestrial networks, for satellite applications, it's very important to have line of sight, especially if using high frequencies and millimeter wave or microwave even. One of the observations we found that the switching between line of sight to non-line of sight for a particular point follows a continuous space Markov chain. Now the probability, that was a very interesting observation, the probability of the line of sight depends on the elevation angle. So elevation angle, let's have a look at here. So elevation angle is the angle between the satellite and the horizon. So the higher the angle, the more likely you will find a satellite. You can find a satellite in the line of sight. So let's look at this line, for example, the yellow line. Let's say at a angle of 70 degrees, it's 80. There's a probability of 80% in an urban environment to have a line of sight. Now, it's just fine. You could at 90 degrees, mean just directly overhead. That will be the best. But the probability of having satellite exactly at the overhead is much lower, of course. Now, if you have a rural environment, the probability improves because you have less obstacles. And what we showed in this model, by the way, was derived based on pure geometry. And it follows very simplified relation here. As you see, there's a function of theta, which theta is the elevation angle. The higher elevation angle, the better line of sight probability. And of course, also depends on if it's rural or is it suburban or urban. So urban has the lowest, rural will have highest line of sight probability. Now we're moving here to a bit more technical depth of how to analyze this satellite constellation. Now, mind, these are very, massive simulation tasks to be taken. What we want to do is develop some kind of intuitive equations that give you some insights of the performance before you go and run a very extensive operational performance. We want to play with the different parameters to design a proper constellation. And we want to see this effect kind of in hopefully in a tractable way to see the relation between input parameters and between the performance of the network. I'm going to explain a bit more here. Now, before I do that, probably, if you haven't heard about stochastic geometry, that's fine. I'm just going to probably provide a quick introduction. For that, I have a box here, 2 by 2 unit of length. Now I have inside that a smaller box, which has a length of 1 by 1. I'm going to drop 100 points. Now, some of these points will fall into the smaller box and some will fall just outside. Now I want you to guess how many points will fall inside. Let's calculate that. So the area of this one is 1 by 1. So it's 1 square unit length. And then the outer one is 2 by 2, which is 4. So the area of the inner shape is quarter the total area. So we should expect about 25 points to fall inside the small one. Let's drop the points. And I'm dropping points now. Let's see. Okay, so we got 28 points fell inside it. So it is roughly about 25%. Now, if I repeat this again and again, obviously for thousands of times, I would get an average of 25 points. However, every time I repeat the experiment, I will get a histogram, a distribution of this point. Now, we call this a binomial point process, and it's as simple as that. So binomial point process follows a binomial distribution. That means the probability of getting some number of points in a certain area. It follows a binomial relation with the probability P, which is the probability that a point falls inside this area, which in this case was 25%. Now, so to make you believe me, I repeated this experiment many times. I'm not going to do it now. I'm going to click play. So this experiment being repeated 5,000 times, and you can see that the empirical histogram follows exactly the probability mass function of the binomial distribution. Now, so how is that related to satellite? I'm going to get there. First, let me show you how is it related to terrestrial networks. You look at this figure, you might recognize that this is an ideal cellular network. So basically, you would like to put a cell tower in the middle, and then put another cell tower with a fixed distance, and then put a third one, and so on. This is called a triangular lattice, because if you connect all the points, they will look like triangles. Now you must say, okay, now I'm seeing hexagons. These are hexagons. They are called the Voronoi tessellation. Means each line here represents an equal distance between two neighboring points. Now again, this is an ideal cellular network. But then let's say I want to go and install a tower at this point. And to my surprise, this point actually is in the middle of a street. So I can't really put it here. So I have to shift it a little bit to the left, a little bit to the right, so I can find a more suitable location for my cellular tower. All right, I want to put this point here. Okay, I found it. Maybe it's in the rooftop of some house, and these people did not agree to put a cellular tower, which is understandable. Then I had to put it on somewhere else. So then the network is not going to be hexagonal anymore. I'm going to play this and I show you how a deformed network would look like. So this is what you actually get most likely in real life. You would never get a nicely hexagonal network. So you can see here this stochastic geometry, which is the field of studying random patterns, comes here into help, because there are a lot of mathematical tools and theories that can help you to deduce, for example, probability of coverage. You can deduce the interference level. The contact distance is the distance to your nearest serving cell, a signal to interference, a lot of beautiful performance indicators you can get. Now, if to believe me, I'm just going to plot for you. This is actually Melbourne, and this is one of the operators which has their cellular tower as open access. You can download them and plot them. And you can see there is no hexagonal network. The network actually looks very messy and very random, basically. This is an example paper showing that if you use So basically, you can predict the coverage of this network just by using nice equations. You don't have to run extensive simulations. So you can see the blue line basically is one network or one model called the Matter-Hard core process, and you can see how it matches at some point with what you expect from a cellular coverage. So the x-axis is the number of frequency groups, or you can call them frequency subchannels, and also the y-axis is the probability of coverage. Now, if you use just random, you just sprinkle this the channels randomly, it's called the post-zone point process, and it provides the lower bound estimation of the coverage. Now, this is not about terrestrial. How is this related to satellite? Let's have a look. For a satellite scenario, we have two very famous constellations. One is called Walker Star. So Walker Star, you have your orbits arranged into orbital planes. And now these orbital planes are near to the pole. So it's about 80 degrees, for example. Example of application using Walker Star is OneWeb, for example. But you can notice there's a lot of crowding near to the poles because all the satellites converge in the pole. While near to the pole, there are no users, so there will be a lot of redundant satellites. The other constellation is called Walker Delta. Walker Delta is used, for example, by Galileo. And if you notice, it also resembles Starlink. Starlink uses largest Walker Delta, but also there are some polar orbits to provide coverage for near to the poles. This constellation is more homogeneous, provide a more homogeneous coverage than the Walker Star. The orbital inclination is about 60 degrees from the equator. Now, when you increase the satellite a lot, you find that it doesn't really matter what orbit you use. And what we come here is we propose what's called the random model of satellites. That means the satellites themselves are homogeneously distributed around the globe. So they actually travel in an orbital shell at the same altitude in this example. Now, the advantage of this network is not because it's practical, but because it's mathematically tractable. You can derive mathematical equations that describes the coverage, the performance using this randomized model. Now, how does this model work and how can we generate it? Because for terrestrial application, no problem, we sprinkle points randomly or cellular towers randomly. But in a satellite scenario, and let me explain a little bit what is this dome. So if you have a user somewhere, so I haven't drawn the Earth, so Earth should be somewhere like this. I have a user on the surface of Earth. This dome is the visible section of the satellite shell, of the constellation shell. This line, which is the blue line, is called the pass arc. So this point where the satellite becomes available is called the acquisition of signal point. The satellite passes through the arc, through the dome, your local sky, and then kind of disappear at the loss of signal point. So the seed point means the satellite where it starts, it's randomized. You can randomize this. You can use the coordinates which called the right ascension and declination point. These are independent of Earth rotation as a seed point. So basically the right ascension would be uniformly distributed around the z-axis, and then the declination will need to follow the arc sign of a uniform distribution between -1 and 1. If you use this distribution, the points will be homogeneous around the satellite shell. Now, after that, you have to throw each satellite in a random orbit. So it's a random circular orbit because most of telecom application uses a very near to circular orbit. These are non-standard parameters. So we derive the equations to convert these non-standard angles into standard angles, which you can use in what we call the satellite propagators. The angles are the inclination, right ascension of the ascending node and the argument of periapsis. These are, people working in satellite applications, they know you can use these angles. These are the Keplerian elements. You can use them in a propagators to predict the orbit. So here's an example of how a random constellation look like when you propagate it over time. I didn't draw the entire orbit because it becomes very messy, but the bottom line is that the satellites are still homogeneous, meaning after 1 hour, you look at the distribution, it's still homogeneous around the satellite shell. So why are we doing all this hassle? Well, as said before, because we could do some analytic approach, analytically tractable equations. I'm going to show you a few examples. This example, if there is a certain user, it picks up the nearest satellite as the serving satellite. So the power arrived from the nearest satellite will be the path loss, which depends on the angle, plus the additional path loss, which we showed before, is called the excess path loss, multiplied by some factor, which is the channel fading. Other satellites are considered, if they're using the same frequency, they will be interfering to the downlink signal. So the sum of all other powers will be considered as interference. There is a mitigation factor. So we're assuming there is a directivity for your antenna. Also, there's some sort of coordination. So the impact of other satellites will be mitigated by some parameters. Now, if you use this model, you can find there's a very nice equation that you can derive from it. And this equation matches the simulation. And I'm just going to explain here. The x-axis here is the power, and the y-axis is the probability of success, mean probability of coverage. Obviously, when you increase the power, you will get better success. But also what you can find here is we're changing the number of satellites. So when you increase the number of satellites, you will also increase the probability of success. So again, it's only using an equation. You can predict if you use certain power, if you use certain number of satellites, you can have a rough idea where to start your analysis, where you start your design of the satellite network. Another example where you could use stochastic geometry is to optimize the altitude of a satellite. So should I put my constellation at 1,000 kilometers? Should I put it at 400 kilometers? Let's see the difference. So at 400 kilometers, I will be able to see less satellites at a given moment, while at 1,000, I will be able to see more satellites. So what's the difference? Which one would be better? Well, there are different factors. One of the things, if you have a higher orbit, there will be more path loss. So you need to keep that into account. There will be more satellites, which is a good thing, but also the coverage footprint will be larger, and that will lead to more interference. So there's kind of a trade-off here and then you'll find there might be some optimal height that I can place my constellation at that balances all these parameters. And well, you can see here in this figure, the x-axis is the altitude, y-axis the probability of coverage. And for a given number of satellites, let's take, if my constellation has 500 satellites, which is the yellow line, there is an optimal point in this particular example, if I use certain IEEE of about 800 kilometers, which will provide the best coverage for the users. Now, again, all these parameters are interlinked. I can change the altitude here, I can change the IARP, and I get different optimal point. So you're just using equations, you can get a very good start to your design of your constellation. Now, the other thing we are familiar with is the Doppler effect. When you have a car zooming very fast next to you, if you ask any small kid what is the sound of a car, and you say it's zoom, because zoom is basically the Doppler effect of a satellite passing next to you. It comes with a high frequency, which is the Z, and then when it passes, it becomes the U, which makes the sound less. Now, this is exactly happening when a satellite passes near to the user. LEO satellites are around 7 to 8 kilometers per second. Here's a user, satellite is passing, and when the satellite is approaching, there's a shift in the frequency, will be higher, and it reaches the closest point, the shift will be 0, and then it will recede, and the shift will be negative. Now, if you use, so this is basically the formula for Doppler shift. Now, if you use geometrical reasoning, you can derive exact formula or approximation of the bounds of the Doppler. So you can just by knowing the height, I'm going to show you an example here. I'm not sure if you can hear the voice, but I did make it as audible instead of course, this is a frequency domain. But if you translate that into audible signal, and you can see here, here's a user and the satellite is passing, and create this Doppler effect. Now, looking at the equations, these are beautiful equations showing that if I approximated, if I considered the Earth kind of very slowly moving with respect to the satellite movement, I can derive the distance, which is called the slant distance. If you differentiate the distance, you get the velocity. So with a very nice and elegant mathematics, you can derive the upper bound of the Doppler. So this is called normalized Doppler, meaning it's hertz per megahertz. If you give me your carrier, let's say 100 megahertz, I can tell you how much would be the Doppler shift. Now, if you look at this equation, let's look at the parameters. RE is the Earth radius. Mu is a gravitational parameter. So this is constant, constant, constant. The only variable will be the altitude. So by just knowing the altitude, I can tell you what would be the expected Doppler shift. And you can look at this graph. X-axis is the altitude, Y-axis is the Doppler shift. And as I go higher, the expected Doppler shift, so this again, hertz per megahertz, so you can consider this as part per million. For example, at an altitude of 1,000 kilometer, my expected Doppler will be around, for example, 22 hertz per megahertz. Now, not only the, so this is all basically basic geometry, but what stochastic geometry can give you is a statistical distribution of that Doppler shift. Now, is that practical? Well, we tried that against OneWeb, and we tried it against Iridium, and there's a very close resemblance between the analytic, it's called the CDF, and the actual empirical CDF. Now, it didn't match for Starlink because of the very difficult constellation, but it matched very well for Iridium and OneWeb. So what does that mean? Just by using a simple equation, you can predict the distribution of Doppler before you even run any simulation. Another example is predicting the path duration. So path duration is how much time does the satellite spend in your local dome. So here's, I'm here. I have my antenna pointed upward. Now my antenna doesn't cover the entire dome, but then the question is, by average, how much should I expect the satellite to last? Is it 1 minute, 2 minutes, 5 minutes? Well, let's see. So what we've done here is also we use stochastic geometry. And I'm not going to go too much in depth into these graphs, but the x-axis, just a summary, is the altitude. Y-axis is the time the satellite spends. Now, for an isotropic antenna, meaning you can receive from any part in the sky, you would note that, for example, the more you go, the higher you go, the longer the satellite will do well in your local dome. Let's take an example of 1,000. 1,000 will give you approximately here, according to the about 14 to 15 minutes from the rise of the satellite till its fall. So this is from the acquisition of signal till the loss of signal. So mind, this is the average. So this could be much shorter, could be longer, and that's how you get the distribution. So using just a simple formula, so this is an approximation. If you just plug the altitude in kilometers, you can calculate the average time that the satellite is going to spend. So why is this important? Because when you're designing, for example, an antenna, or when you're designing your steerable antenna, you need to know roughly how fast you want to steer this antenna, either mechanically or electronically. Now, electronic will be less of a problem, but mechanically, you can calculate even how much the motors will last based on such average calculations. Another example is the handover analysis, because you can't just use one satellite. You need to use from one satellite multiple beams. You saw the beam pattern for example at the beginning. So you had so many beams, so you have to switch between different beams, but also you have to switch between different satellites. So one strategy, for example, here's my serving satellite. Keep tracking of that satellite within, let's say, 5 minutes, and then I lost the satellite. I will go to the next available satellite, or which is closest to the zenith. One example, because we'll have the strongest signal. I can go to another satellite. So it depends on your handover strategy. This is one strategy. Another strategy is you keep track of the closest satellite to the zenith. So zenith is the point above the user. So the user is somewhere here. And then as soon as another satellite becomes closer to your serving satellite, you switch to that satellite. Now, these are two arbitrary handover scenarios, but using stochastic geometry, you can model the handover time, and that's a very important parameter when you design a network, because every time you do a handover, you need to do a lot of signaling between the satellites, and that is a cost. That's an additional overhead into the network because you need to wait until the network reestablished a new connection. So here's one more example on the optimization of the beam of the satellite. Now, this is a nice simulation. I want you to look at the beams and see what's happening here. We are increasing the sizes of the beams. So first at the beginning, let's just go back. So you had very small beams, and this is not good because all these areas are not covered between beams. Now, if I run the simulation, I'm increasing the beams, and at some point, okay, so you had almost full coverage. But if I kept increasing the beam, what's going to happen? Satellites will start interfering to each other. If you have very large beams, mean your frequency will spill into nearby beams. So what is the optimal beam that I need to use? Well, this is another thing that you could use stochastic geometry to help you decide on that. I'm going to just explain that a bit. Maybe not the details. You always feel free to go to the paper to see the details. But let's look at, we have three scenarios. We had an omnidirectional satellite. I mean, a satellite has a sufficiently wide beam width to cover a little bit more than the horizon. You have a user which can also accept coverage from hemispherically. Now, effectively what you'll be limited by is the curvature of Earth. So that's occlusion limited or curvature limited. The other scenario that the satellite has a smaller beam, the user has a wide beam, but then you are limited by the satellite. A third scenario is you have a satellite, you have a satellite which has a wider beam and than a user, but the effective beam would be user limited or device limited. Now, why we're introducing this? Because if you have different beam width and you look at the coverage, again, higher beam, you can provide more coverage area for a small number of satellites, but also will start introducing more interference. So you see there's a sweet point where you can balance the coverage and interference, which we can derive just by using mathematical equation. This is what the paper was presenting. And this is the last application I'm going to present, which is the eclipse. This is not a telecommunication application, but very interesting because it uses very similar concepts. Now, this is not a picture to scale. Sun is much, much further than Earth than this picture, but we just put it here for illustration. So what you will find here that in a low Earth orbit environment, satellite passes go through a night and day so many times in a single day. So it goes through the shadow of Earth, go back to the sun, and then go to the shadow. Now, every time it goes to the shadow, it has to use its batteries. Every time it goes to the sun side, it has to recharge. So what does that mean? You have a lot of charging, recharging cycle. You would like to know at least how many of these cycles I'm expecting. What is the statistical distribution of that? So if you look at the random model, this is this area here, the covered area is the umbra, or the area with the shadow of Earth, and these are the shadowed satellites. Now, satellites are moving very fast. Can we use stochastic geometry to provide some prediction? Well, it end up, yes, you could use it. I'll just show you here a quick example. The x-axis is the altitude of the constellation. The y-axis is the average time the satellite is eclipsed. So let's take, for example, 1,000 kilometer. The satellite is going to be eclipsed for 26 minutes by average. So when you design your battery, this number will be very important because you need at least to cover the satellite for the duration that it is in the eclipsed side. This figure shows you the satellite altitude versus the number of eclipses you can get per day, the average number. So for a height of 1,000, you get about 12 eclipses per day. So you will go into charging, recharging cycle 12 times. Now, again, using stochastic geometry, you can obtain the distribution. I didn't put the function here of the distribution, but you feel free to go to the paper and see it. And it matches, actually, doesn't match, but it kind of gives you some indication based on this equation. It gives you an indication that how a practical network, for example, a Walker delta, would behave. So this is basically the CDF. The x-axis is the eclipse time, and the y-axis is the CDF of that time. Now, what other applications we could use the statistical tool to analyze? Well, there are many applications. First is the delay performance. You can calculate, for example, how much delay would I get if I communicate between a point in Australia and a point in Europe if I use different maybe routing strategies. So you can statistically obtain the distribution of the delay. You can explore different diversity strategies. This is also being presented in a paper. You can also explore different spectrum sharing. Again, spectrum sharing is very important because it's a finite resource. And then you can explore if you want to share it between GEOs, LEOs, terrestrial networks, etc. And obviously the non-line of sight, the non-terrestrial network line of sight modeling. So takeaway, few points. Mega satellite networks, they're bringing, bridging the digital divide, we hope, in the near future. They fill the remaining gap of coverage. The other thing, there are a lot of opportunities and challenges. One of the challenges is integration with terrestrial networks. We would like to have one phone, and this phone works for terrestrial networks. You take it to some very far rural area, and you still have coverage. So we would really like to have that. So this is something that very actively being worked on by 3GPP and satellite operator. Spectrum availability, remember, is a finite resource. It has to be coordinated very carefully between different operators, between GEOs, LEOs, and terrestrial. We also want fair access to space. That's very important, and secure and reliable. Again, you don't want to keep just one company or one person controlling all these networks. You need to have it more democratized and with more access to a lot of people. Exciting new technologies such as direct to device, which will say you can use your cellular network directly to the satellite. Inter-satellite connection will reduce the number of gateways. And nice new applications. Since you are sending satellites, you can use them for sensing, for example, Earth observation. You can use them for environmental monitoring, etc. What we showed in this presentation, that there is a nice tool, statistical tools they can use for tractable performance analysis. Now, that's it from my side. Thank you very much for listening, and I appreciate that. Open for questions.